closed loop or for the open loop system, eventually the system will approach to 0. And that is our desired response, because for our input command, eventually our system will be 0. Okay? So for this input is okay. Then I'm going to erase this one to do the second scenario. Any questions before I erase this? For the second scenario will be the unit step input. And this is 1, so this is 1/s. Any question about here?
Yeah. So how can the input be negative?
How can input be negative?
Yeah, the unit impulse.
Unit impulse is just, if you like, you can have, for the negative unit impulse, if we like to control a system like rotating system, then positive unit impulse is like this, negative is like this. But in terms of this one, I don't know how to apply to it. Okay. So without any more questions, then let me proceed. This one here. So for the second scenario, then the RS will be equal to 1/s. Okay, and then this one we can do the factorization as over A. From here you can see pretty much your homework you have done pretty much can support the detailed calculation here. So basically I would say right now everyone should be in good place, in good positions. Then the remaining is I need to give you the terminologies and the methodology how to analyze the system. But I think most of the calculation I pretty much I have to get yourself ready here. Okay, so for this one we can do the calculations. So here we see, okay, here is my scratch calculation, s, 2s plus 1. So here is 1 will be equal to s, 2s plus 1. I don't have a preparation in my lecture notes, so I come up here. So that will be 2as plus a plus b squared plus cs. So here we compare the coefficient here. The square term will be b equal to 0, and this one will be equal to 2a plus c. Then we compare the constants, so that means a will be equal to 1. Okay, so from here c equal to minus 2. So this one a equal to 1, c equal to minus 2 here. Any mistakes? Whatever. Yes, I think the result is right. Okay, so here the omega O, we take the inverse Laplace transform. For this one, that will be equal to inverse 1/s plus inverse minus 2, qs plus 1. So here this one will be equal to this one, the inverse Laplace transform of this one equal to 1. And this one is minus 2 times, let me do one more time here. So this is the inverse minus 1 as plus 0.5 here. I just transform it into the standard form in the tables. So this will be minus e minus 5e. Okay. So now for this one, that is s plus 1, s plus 2 times s1 here. And for this one, again, we can factorize as a and s plus 2, b as plus c. The same thing here, we compare. A as plus 2 plus b as squared plus c. So s squared, b equal to 0. So as one term, a, c A plus C equal to 1 square term AS plus 2A, sorry. So 2A equal to 1. So from here, the A equal to 1/2 and C equal to 1/2. Okay. So therefore, the omega C over T will be inverse 1/2 S plus inverse 1/2 S plus 2. So this will be equal to 1/2 and plus and 1/2 E minus 2. So now again, we can draw the response here. Okay, the black line is our input, unit impulse response. Is it equal to 1? Okay. And for this one, you can see this is a superposition of 1 minus this. So this profile is omega OT. This is the exponential profile of 0.5t. The reason why here is here. You can see for this one, based upon this one, you can see when t equal to 0, omega O t equal to 0, right? So then you can say say t equal to 0.5. You can do the tracking a few dots. You can quickly draw a good curve here. So the same thing here. Omega ct. So here when t omega ct. So when t equal to 0, this value equal to how much?
1.
Equal to 1. And when t equal to a little bit, say 1, then this value equal to 1/2 plus 1/2 times certain smaller number smaller than 1. So here that is starting from here, and then let me do this. So this is time, and this is 1/2. Superimposed onto 1/2, we have this value exponential 2t here.
Negative 2t, yeah.
So here, the output should be like this. For the output, eventually it will converge to a value which is equal to 0.5 here. Okay, for example, here you look at this system. When t equal to infinity, this value equal to 1/2 here. Okay? So for these systems, if we use the system to track the unit step input, our desire is to have the response to go with the one, this black line, as quick, as close as possible. But from here you can see the output, the closed loop system seems is worse than the open loop system. The open loop system eventually will converge to 1, and then the output will converge to 0.5. Unless my calculation has certain mistakes, then the closed loop system for picking up this number is not okay. Okay. Then for the third scenario, then here I won't repeat, but I can give you for the third scenario is this. You can do it on your own, and we call the unit ramp. Unit ramp input is this. This is time. This is input. Basically, it is velocity tracking. The slope equal to 1. So in preparations, RT will be equal to T. Okay, then which means the RS will be equal to S squared 1 over S squared. Okay. So with this one, you can repeat the calculations and see and how that goes. Okay. So here, that is the details. And again, for all the calculations, I don't think there's something new here. All the first two homeworks, basically, the skills you have to learn should be able to support yourself to develop the kind of the strategy to study what is the difference between the two systems. Okay, so here I show you the detailed work. So this is the curve provided by our textbook in figure 4.13. So here they pick up a value tau equal to 10, which is different from 1. And K1, K8, K2 multiplication equal to 100. So basically here you can use the numbers and you can repeat the calculation. The textbook didn't provide us the detailed calculation, so that's the reason why here I show you the details here. So with those numbers, you don't feel surprised how come the curve will be like this, because the textbook provides, I think the authors kind of played around a little bit and found a combination of good numbers. You can see for the closed loop systems, for the unit impulse for this scenario, okay, for this scenario, the closed loop system can track the unit impulse so quick, eventually go to 0, go to that value so quick. Compared to the open loop system, it's like this. Okay, so the open loop system, you can see that is the profile is like this, just like this. Okay. Once you have the MATLAB programming, then you can just tune the numbers very easily, very quickly. You can study a lot of the scenarios here. Okay. For this case, I believe that is go to the unit step input response, and he didn't say it here, but basically that's the unit input response. Okay, and pay attention for the open loop system. It's saying it will take about 40 seconds. 40 seconds to reach 1. So, for example, if you are the pilot and engage in the air fight, then for some reason the airplane you assigned to pilot have such response, then basically you serve for your country as the target for exercise. Everyone will salute you. Because you want to turn, say, you want to divert from the track, then you will have to wait 40 seconds. You know what I mean? Okay. Sometimes the system will respond so quickly, so abruptly, and we will have the overshoot here. We try to reach as quick as possible, but overcompensate it will go overshoot and coming back here. And if you've seen your vibrations, have you seen that vibration? You have kind of the peak oscillation, and that is the one here. Okay, so that's the different numbers you tuned, and then you have the different response here. So this is the one example here. Before we move on to the error analysis, basically this is end up our kind of the transient response analysis using examples here. Any questions before we move on to the second topic? Should be straightforward, right? So basically just do the calculations. Then at this moment you may ask me, okay, so how can we quantify the response? So for example here, like I mentioned, certain system will respond so quickly, it will overshoot and coming back here. So overshoot will be one measurement to the system's performance. And how quickly the system will rise to 1, that's another measurement to indicate the system response. And we have other more. So in chapter 5, we will totally dedicate ourselves to learning a more quantitative approach to measure how good the system is. Okay, so here we stop here for this one. The next one we're going to move on to is the error analysis. Error analysis will be focused on here. Rather than showing the output response to the input, here the error analysis we want to show is how the dynamics of the error will approach into 0, which means the output will be identical to the input. Okay, so here is a different perspective of studying dynamic systems here. So here this is the open loop system and output, input. So in our textbook and in our slides, I will use an O again to denote that is for the open loop system, and for C and to denote the closed loop system, just like we exercised. Okay. And if you have printed out your handout, I have a typo here, and please correct that one. So again, the slides here showing is the calculation we have done here. Okay, so the errors can be contributed by the 3 inputs here. And that is our command, control command, our command input. And this is disturbance, and this is noise. Okay. And usually the people classify the disturbance is a signal to disturb the system, for example, the flight. And noise is the signal to disturb, for example, your controllers, for example, your electronics. So that kind of classification of this one. Okay. So this page we're down here, and so for example here, say we only want to study the input, the relation between the command input and the errors. So we're assuming that we can ignore the influence from disturbance. Also, we can ignore the influence from the noise. So we simply take away the 2 terms, okay? Because here these are linear systems, we can superpose the influence of individual terms. So here we only study this term here. So on this page, from this page onward, then we will talk about the error analysis. Here about the closed loop system. Here is a closed loop system. This is the transfer function of the closed loop system. We only concerned about the relation between the 2. Okay. So again, here we want to do the error analysis. We want to know the response of the error to input. So how can you proceed? The same thing, just like our scenario here. You can try the 3 scenarios, the unit impulse, unit step input, and unit ramp input. Because those 3 scenarios are the most basic. And you can linearly superpose them together to come up with more complicated, the 2nd degree polynomial inputs. Okay, most of the control inputs are falling into these kind of 3 categories. Most of the control inputs. Okay. So again, so once we have this, and say if you know your system's dynamics, and then if you know your the controllers, then you can design your inputs, and then you can proceed to calculations. So to do the error analysis, and again, if you have the transfer functions like we have done here in the previous page, just like this is a transfer function, this is another transfer function, then you can repeat the calculation. You will be able to calculate or to plot the curve for the transient response. Okay, we call the transient response is the response of the system in a finite period of time. That is the first one. Okay, the second approach is we want to study the steady state response. Steady state response is when time equal to infinity. So keep in mind, right now I have given you the two methodologies to analyze the system response. Write it down. Two categories. One is the transient response. Okay, so to quantify the system dynamics, which means to measure everything you want, we have two methodologies, and the two methodologies are basically address the different concerns. The first one is the transient response. Transient response is we want to know how the system will track, will approach into the command, and in a certain period of time, and that basically can be seen by the curve. We can see how the curve approaching to the command. The approaching process is the transient response. So that is the first concern. And sometimes people will go to the perpetual response, which means the steady state response. Steady state means the when time approaching to infinity. So that means is that pretty much is, you can say that is what is the system looks like at its equilibrium situations. It's not equilibrium, basically just steady state response. Okay. So here in these calculations I've shown you, and also in your exercise you know the techniques, how to do the calculation, the function of t, function of time, and that is what will provide you the transient response information. And also, for the second category, steady state response, and I have given you in one homework, right? A quick question is how the steady state response is the value of something. So basically, is whatever your transient response will be, you simply take the value t quotient, go to infinity, and then you simply calculate whatever the response, and that is the way to do it. Again, right now our focus on this page onwards is about this. So to calculate steady state response, again, you can proceed in this approach. You simply calculate or formulate the expressions of the systems in terms of time, and you set up time equal to infinity, just do the calculations. To this point, you pretty much spend 20 minutes, right? A quick approach is this formula here. For any response, so for example, say you want to know the perpetual response of anything. Here, for example, is our dynamics, our aerodynamics. So again, this is a quick formula. This one will save you 20 minutes. Pay attention here. If you kind of do it now or watch your finger palms line or whatever, pay attention to here. Okay, I wait for someone to take a deep breath. for whatever the dynamics, that is called the steady state response of dynamics. Here, for this example, is aerodynamics. The steady state response is equal to the Laplace transform multiplied with s, and you set the value of s equal to 0. So, for example, let me calculate using this one for calculations. So, for example, here, and I want to calculate the steady state response. The steady state response of omega ct, then pretty much is we're going to calculate its limit when t approaching to infinity, assuming you haven't proceed the bottom calculation. To this step, once you have a transfer function, then you can proceed. And let me be more precise here. And response to r as equal to 1 over s here. Okay. So now we can do this one. We plug in that equation here. So that will be equal to is we're going to calculate time approaching to infinity, and then omega ct, and due to unit step input. Okay, because this one is our unit step input. So for this one, we simply do the calculation. Is limit as equal to 0 s times omega cs. Okay, so that one we do the calculation as approaching to 0 s. Omega cs simply plug in here as +1, as +2, and what is the rs is 1s here. Okay. Okay, this one equal to this one. So now we can quickly do the calculation. This is 1/2, and that is what we got here. Okay. So here is this formula. If you remember, this one is from our the day one, the table of the Laplace transform. I provide that one to you. Let's call the final value theory in Laplace transform. So the remaining, I think, continue on Wednesday. We will continue on this page to do more detailed calculation.